The moon is one of the most studied heavenly bodies, thanks to its proximity to the Earth. However, it is shocking that latest discoveries by China reveal that what we have been told about the moon is not even close to the truth. What has China discovered about the moon, and how is the truth finally coming out now? Stay tuned to learn what China recently revealed about the moon. China's space program has a long and complex history that spans over 6 decades. China's space program began in the 1950s, partly as a reaction to the fears that the US and Soviet Union would soon be launching weapons into space. China also wanted to develop its own nuclear and missile capabilities to defend itself and gain respect from other countries. Enlisting the help of the Soviet Union, China began to develop its first ballistic missile and rocket programs in the 1950s. However, the cooperation was not to last and ended in the 1960s due to political differences, and China had to pursue its own path to space. China launched its first satellite, Dongfang Hong 1st, in 1970, becoming the 5th country to do so. China's human spaceflight program started in the late 1960s, but faced many challenges and delays due to political and economic turmoil. It was not until 2003 that China sent its first astronaut, Yang Liwei, into orbit aboard the Shenzhou 5 spacecraft, making China the 3rd country to achieve human spaceflight independently. The Chang'e 1 mission marked a significant milestone in China's lunar exploration ambitions. Launched in 2007, it was China's first lunar probe, and its success paved the way for subsequent lunar missions. One of the primary objectives of the Chang'e 1 mission was to provide a detailed, high-resolution map of the lunar surface. The mission successfully captured images of the entire moon's surface with a resolution of 120 meters. This was vital for both scientific research and the planning of subsequent lunar missions. Chang'e 1's onboard gamma and X-ray spectrometers enabled the probe to detect and analyze elements present on the lunar surface. This provided valuable insights into the moon's composition, helping scientists better understand its formation and geological history. And with the help of its laser altimeter, Chang'e 1 was able to study the topographical features of the moon's surface. This gave scientists crucial information about the moon's mountain ranges, valleys, and other geological features. Chang'e also played a pivotal role in examining and recording the space environment between Earth and the moon. The probe gathered data about solar winds and their interaction with the lunar surface, providing insights into space weather and its effects. And beyond scientific achievements, Chang'e 1 demonstrated China's capability to design, launch, and operate complex missions beyond Earth's orbit. In fact, the successful operation of Chang'e 1 reinforced China's status as a major spacefaring nation. The Chang'e 2 mission was a pivotal step in China's lunar exploration ambitions. As a continuation of the Chang'e 1 mission, Chang'e 2 was tasked with more refined objectives and was equipped with advanced technologies to accomplish them. The discoveries and observations made by Chang'e 2 brought new insights into the lunar environment, paving the way for future lunar exploration. One of the significant tasks assigned to Chang'e 2 was to prepare for a soft lunar landing for future missions. To that end, it provided high-resolution imaging of the proposed landing sites. This imaging was not just to understand the topography, but also to ensure that subsequent missions like Chang'e 3 had a safe environment to land.
We know the lander is going to work for at least a year.
The resolution of the camera was approximately 7 meters, in stark contrast to Chang'e 1's 120 meters. This provided extremely detailed images of the moon's surface. The imaging revealed a plethora of geological features, including impact craters, mountains, valleys, and regolith composition. It sheds light on the various stages of lunar evolution. The high-resolution imagery offered more detailed visuals on the distribution of craters across the moon, which can help in understanding the moon's age in certain areas, as regions with more craters are often older. Another critical discovery was the depth of the lunar regolith. Chang'e-2's microwave radiometer was equipped to measure this, and it found the depth to be more varied than previously thought. In certain areas, the regolith was as shallow as 4 meters, while in others, it was up to 12 meters deep. This information is crucial for understanding the moon's history and for any future lunar base construction, as regolith depth can affect building stability. Chang'e-2 also observed the moon from various angles, enabling a three-dimensional mapping. This 3D mapping was vital to observe the height, width, and depth of lunar features accurately. This detailed mapping was not just limited to the front side of the moon. Chang'e-2 successfully accomplished a complete mapping of the lunar surface. This complete mapping has implications for scientific studies related to lunar geology, and also for future human missions, as it helps identify potential landing and exploration sites. One area of special focus for Chang'e-2 was the South Pole Aitken Basin, one of the largest known impact basins in the solar system. Understanding this region is pivotal because it exposes ancient lunar crust and potentially provides a window into the moon's mantle. Preliminary data from Chang'e-2 indicated various compositional differences across the basin, hinting at a complex history of impacts and volcanic activity. While imaging was one of the significant aspects of Chang'e-2, its ability to detect the elemental composition of the lunar surface was also instrumental. Using its X-ray and gamma-ray spectrometers, Chang'e-2 examined the moon's elemental composition. It confirmed data from Chang'e-1 about the distribution of elements like magnesium, aluminum, silicon, calcium, titanium, and iron. These data are essential for understanding the moon's formation and its geological history. Additionally, Chang'e-2 provided insights into the moon's magnetic field. The moon has a much weaker magnetic field than Earth, and its origins remain somewhat mysterious. Data from Chang'e-2 added to scientists' understanding by mapping variations in the magnetic field across the lunar surface. China's Chang'e-3 mission was another significant advancement in lunar exploration. Unlike its predecessor, which was primarily an orbital mission, Chang'e-3 consisted of both a lunar lander and a rover, Yutu or Jade Rabbit, making it China's first attempt to land a spacecraft on an extraterrestrial body. This step forward allowed for a more direct analysis of the lunar surface, complementing the data obtained by Chang'e-2. The Chang'e-3 mission landed in the northern part of Mare Imbrium, one of the larger seas or basaltic plains on the moon. This region was chosen because it is relatively flat, which increases the chances of a successful landing, and because it holds geological interest. The area has a relatively young age in lunar terms, with a history spanning around 3 billion years. By studying this terrain, scientists hope to gain insights into the moon's more recent volcanic activity and the sequence of events that led to the formation of Mare Imbrium. One of the primary objectives of the Chang'e-3 mission was to study the composition of the lunar surface in its landing area. Using its onboard instruments, including an alpha particle X-ray spectrometer and an infrared spectrometer, Yutu provided detailed information about the elements and minerals present. It found that the regolith in the landing area was rich in elements such as magnesium, aluminum, silicon, potassium, and sodium. There were also traces of titanium and chromium, hinting at the complex geology and history of the Mare Imbrium region. Yutu was equipped with ground-penetrating radar, or GPR, which was used to investigate the structure of the lunar soil and crust down to a depth of several hundred meters. This was the first time such an instrument was used on the moon. The data obtained provided a stratigraphic profile of the lunar layers, revealing details about the depth and distribution of the regolith and the underlying bedrock. This information is crucial for understanding how lunar surfaces evolve over time and for planning potential future moon bases or resource extraction. Beyond its instruments, Yutu was equipped with cameras that allowed it to capture detailed images of the lunar surface. These images, combined with direct observations from the lander, provided panoramic views of the landscape and close-ups of rocks, impact craters, and other geological features. These visuals not only helped scientists study the morphology and structure of the lunar surface in this region, but also aided in planning Yutu's navigation, and determining the best areas for further study. The Chang'e 3 mission provided an opportunity to study lunar rocks directly. Several large rocks in the vicinity of the landing site were analyzed using U-2's onboard instruments. The results indicated a diverse range of rock types, including basalts that are different from the samples brought back by the Apollo and Luna missions. These rocks are believed to have originated from deep within the Moon, offering insights into the Moon's internal structure and its volcanic history. While U-2 explored the surface, the Chang'e 3 lander was busy making its own set of discoveries. Among its instruments was an ultraviolet telescope designed to carry out remote sensing observations. One significant achievement was the measurement of the thin exosphere of the Moon, particularly the levels of neutral species like helium, neon, and argon. Understanding the composition and behavior of the lunar exosphere can provide insights into the processes that govern the thin veneer of gases surrounding the Moon and their interactions with the solar wind. In addition to studying the Moon, the Chang'e 3 mission also took the opportunity to observe the Sun. The lander's ultraviolet telescope conducted observations of the Earth's sun, capturing images and data about solar flares and other phenomena. Given that the Moon lacks a magnetic field and substantial atmosphere, it offers a unique vantage point for such studies, devoid of interference that might be present on Earth. One indirect discovery of the Chang'e 3 mission was how well the lander and rover could survive the extremely cold lunar nights. With temperatures plunging to around -180 degrees Celsius, the lunar night presents a significant challenge for space missions. However, the Chang'e 3's systems, particularly the radioisotope heat source, ensured that both the lander and U-2 survived multiple lunar nights, thereby extending their operational life and enhancing their ability to gather data over an extended period. The Chang'e 4 mission has been one of the most significant lunar explorations in recent years, particularly due to its targeted destination, the dark or far side of the Moon. This part had never been previously explored at the surface level by any other nation. The primary objective of Chang'e 4 was to understand the topographical and mineralogical differences between the near and far sides of the Moon. Its landing site, within the South Pole Aitken Basin, is believed to be one of the oldest impact structures in the solar system. The exploration of this location was expected to provide insights into the early history of the Moon, and even some information about the origins of our solar system. The U-2 rover, which accompanied the Chang'e 4 lander, relayed detailed surface images and data. These showed variations in the lunar landscape, including a multitude of impact craters of varying sizes, rocky outcrops, and regolith plains. This rugged landscape is a testament to the tumultuous history of the Moon, shaped by cosmic collisions. One of the prime discoveries of the mission was the identification of materials that are not common on the Moon's near side. For instance, U-2 identified rocks that appeared to be chemically different from those found on the near side. Preliminary analyses indicated these could be composed of mantle material, potentially brought to the surface by the very impact that created the South Pole Aitken Basin. This discovery could have significant implications for our understanding of the Moon's early geological history and the processes that differentiated its crust and mantle. The Chang'e 4 mission carried instruments to measure the surface temperature over the lunar day and night. Data showed that during the lunar night, the surface temperature can plunge to about -190 degrees Celsius, or -310 degrees Fahrenheit, while in the lunar day, it can rise to roughly 200 degrees Celsius, or 392 degrees Fahrenheit. These extreme temperature variations have implications for future lunar missions and the potential for sustainable lunar bases. One of the unique advantages of exploring the Moon's far side is the absence of radio interference from Earth. The Chang'e 4 mission took advantage of this by incorporating a low-frequency radio astronomy experiment. Observations from this experiment provided a clearer and less disturbed picture of the universe, which would be near impossible to achieve from the Earth due to our planet's ionosphere and the plethora of human-made radio signals. In a miniature biosphere experiment, Chang'e 4 carried seeds of cotton, rapeseed, and potatoes, as well as fruit fly eggs and yeast. The idea was to observe whether a mini biosphere could sustain itself on the moon. While initial reports indicated that the cotton seeds had sprouted, making it the first known instance of any biological growth on the moon, the sprouts did not survive long. The significant temperature variations, among other factors, made it challenging for life to thrive. Despite the short-lived success, this experiment has paved the way for future experiments on life sustainability in extraterrestrial environments. While Chang'e 4 itself did not directly discover water ice, its landing in the South Pole Aitken Basin added momentum to the exploration of the moon's poles, where previous missions had hinted at the presence of water ice in permanently shadowed craters. The existence of water ice on the moon could be crucial for future human exploration and colonization efforts, as it could be used for drinking or split into hydrogen and oxygen for rocket fuel or breathing air. The U-22 rover carried instruments to study the properties of lunar regolith, or moon dust. Lunar dust is known to be particularly abrasive and could pose challenges for long-term human missions on the moon. China launched the Chang'e 5 mission in 2020, with the primary objective of the Chang'e 5 spacecraft being to return moon samples to Earth, which it successfully achieved. The samples retrieved were found to be relatively young, approximately 2 billion years old. This discovery is crucial as it provides insights into the events that transpired late in the moon's history. Moreover, understanding these events can shed light on the evolution of Earth and the broader solar system. The Chang'e 5 mission's significance, however, extends beyond just sample collection. The samples from the moon offer a unique opportunity to study the moon's history. The moon's surface, dotted with craters and splotches, tells the tale of the early tumultuous days of our solar system. These scars are remnants of the numerous asteroids and comets that collided with both the moon and Earth. Such impacts are believed to have brought water to Earth, a critical component for the emergence and sustenance of life. To piece together the moon's history, scientists study the age and composition of different lunar regions. While orbiting spacecraft can gather a plethora of data, certain scientific experiments necessitate Earth-based instruments. These instruments are often too large and consume too much power to be deployed in space. Moreover, conducting experiments on Earth allows for repeatability in various labs, and the samples can be preserved for future generations to study, using potentially more advanced technologies. Chang'e 5's landing site was in Oceanus Procellarum, also known as the Ocean of Storms. This is a dark gray region located in the moon's northwest corner and is visible from Earth. Specifically, the spacecraft landed near Mons Rumker, a 70-kilometer-wide mound. This site was chosen because it was believed to house young rocks and soil, the result of a significant volcanic event that concealed the original surface. The samples analyzed on Earth from this site were found to be around 2 billion years old. In comparison, the samples brought back by NASA's Apollo astronauts were much older, ranging between 3.1 and 4.4 billion years. The Chang'e 5 mission employed a complex architecture reminiscent of NASA's Apollo missions. It consisted of 4 main components: a service module, a lander, an ascent vehicle, and an Earth return module. Once in lunar orbit, the lander and ascent module descended to the moon's surface, while the other 2 modules remained in orbit. The lander was responsible for collecting the samples, amassing 1.7 kilograms, using both a mechanical scoop and a drill capable of reaching 2 meters below the surface. Additionally, the Chang'e 5 lander was equipped with 3 scientific payloads. These included a set of cameras to document the landing site, a ground-penetrating radar to map the subsurface, and a spectrometer to study the mineralogical composition of the landing site. This last instrument was particularly crucial for determining the amount of water present in the lunar soil. After the sample collection, the ascent vehicle was launched from the lunar surface to rendezvous with the service module in orbit. The samples were then transferred to an Earth return capsule. This capsule re-entered Earth's atmosphere at speeds much higher than those returning from low Earth orbit. To manage this high-speed re-entry, Chang'e 5 employed a skip re-entry technique, where it bounced off the atmosphere once to decelerate before making its final descent. The capsule safely landed in Inner Mongolia, the same site used for China's crewed Shenzhou spacecraft returns. Following its primary mission, Chang'e 5 embarked on an extended mission. It first traveled to the Sun-Earth Lagrange Point 1 or L1, a point where the gravitational forces of Earth and the Sun balance, allowing spacecraft to remain stable for extended periods. This location is ideal for solar observations. After conducting technology tests at L1, Chang'e 5 then moved back to the Moon, entering a distant retrograde orbit or DRO to test technologies for upcoming Chinese missions.